Please subscribe to support the channel. Okay, how long? Really? Saturn is not just far, it is off scale for everyday sense. At the best alignment, it sits a little over 1.2 billion kilometers from you. At the worst, it pushes past 1.7 billion. That's roughly 8 to 11 times the Earth-Sun distance. Even light, which sets the speed limit, needs about 80 to 90 minutes to cover that gap. You send the signal, you wait more than an hour for a reply. Right away, you see why "just go faster" is not a plan, it's a slogan. Now set a baseline you can trust. If you want the minimum energy route, you leave Earth's orbit and slide onto a stretched, sun-centered path that touches Saturn's orbit on the far side. This is the classic transfer you learned first, and it is slow by design. You're not punching straight lines through space, you are changing orbits under the sun's gravity. Do that careful move and you get a cruise near 6.1 years. That number is not guesswork. It falls out of the geometry and the gravitational pull you live in. It's the floor if you care about efficiency and payload. History shows the trade in real hardware. Voyager 1 launched in 1977, grabbed a major speed boost from Jupiter, and reached the Saturn flyby in about 3.2 years. It was fast because it never tried to stop. Voyager 2, different timing and path, hit Saturn in about 4.0 years. Then there was Cassini. Cassini was built to stay, map, and work for years. It used a sequence of assists. 2 at Venus, 1 at Earth, 1 at Jupiter, then arrived in 2004, about 6.7 years after launch. Those two timelines, roughly 3 to 4 years for a flyby and roughly 6 to 7 for an orbiter, are not contradictions. They are different mission goals, different energy budgets, different mass delivered to the target. Arrival is where the real bill shows up. If you want to orbit Saturn, you must slow down relative to Saturn. There is no external brake waiting for you. Cassini performed a Saturn Orbit Insertion burn that lasted about 96 minutes, trimming speed by around 626 meters per second relative to the planet. That single maneuver was mission critical. If the burn had failed, Cassini would have flown past and the orbiter campaign would have ended before it started. Keep that in mind because every plan that saves time by arriving faster makes this burn harder, longer, or heavier, unless you bring another braking method. So when you ask how long it really takes, the honest answer is a range controlled by 4 levers. First, alignment, because the positions of Earth and Saturn set when the efficient windows open and how much extra energy you must spend if you miss them. Second, energy, which shows up as the launch vehicle's performance and the departure speed you buy on day 1. Third, gravity assists, which let you trade momentum with other planets and cut calendar time without hauling as much propellant. Fourth, arrival strategy, because stopping to work in the Saturn system forces you to pay the braking cost one way or another. Put those together and you get a clean map. Take the minimum energy path, live with the calendar, and you land near 6 years. Want a quick look and no stop and you catch the right Jupiter window, then 3 to 4 years is proven. Want to orbit with current chemical rockets and real science payload? Expect on the order of 6 to 7 years, depending on window quality and your capture plan. Want to squeeze harder with big departure energy and minimal mass? You can trim that, but you start sacrificing payload and margin, and you raise the stakes at arrival. This is why expectations often break. Distance by itself does not set the schedule. Energy does. Geometry does. The arrival plan does. The clock on a Saturn mission is not a single knob labeled speed. It's a panel of choices that push and pull each other. You can buy calendar time, but you pay in propellant, in launch mass, in navigation complexity, and in the risk that the final burn has to be bigger than your margins like. So here's the working headline for the rest of the series. With today's standard chemical tech, a practical orbiter sits around 6 to 7 years. A fast flyby can be about 3 to 4 years. And more exotic approaches can move those numbers, but only by accepting serious engineering challenges at launch and at arrival. That's the frame. From here on, we drill into the mechanics of why those numbers land where they do and how mission designers actually pull the time down without killing the payload or the science. If you can't just point the nose at Saturn and floor it, what are you really doing during that 6-year floor? What rules set that timing? And how do launch windows, relative speeds, and the price tag number engineers use all lock your schedule in place? Why can't you just aim at Saturn and floor it? Because you don't fly straight lines in the solar system. You fall under the sun. The real path is a transfer ellipse with its near point near Earth's orbit and its far point out at Saturn's. The size of that ellipse is basically the average of Earth's path at 1 astronomical unit and Saturn's path at about 9.5, so a bit over 5 astronomical units. Bigger orbits take longer in a very specific way. The period grows faster than the size, and your travel time is half of that period. Do the math and you land near 6.1 years. That's the slow, efficient cook. It isn't a guess, it's what gravity gives you when you spend the least energy and accept the calendar. If that's the shape, when do you leave? Launch windows are not marketing, they are the product. Earth and Saturn line up usefully roughly 378 days. In a good window, the ellipse you ride meets Saturn right when Saturn gets there. Miss by a few months and two things happen. Either you wait for the next window, which can shove the whole mission a year, sometimes more once you refit schedules and team availability, or you try to claw back the miss with extra energy, which makes the rocket bigger, the payload smaller, and the arrival hotter. This is why mission planners publish narrow, instantaneous launch times inside multi-week ranges, then stress over every scrub because a slip of days can cascade into months or years of consequences. Speed is not absolute here. It's relative to the sun. At Earth's distance, you're already moving around the sun at about 29.8 kilometers per second. Saturn moves more slowly, around 9.7 kilometers per second, because it is farther out in a weaker gravitational well. When you go to Saturn, you are not just gaining distance, you are changing the shape and the speed of your path around the sun so that out at Saturn's distance, you meet the planet with the right direction and a manageable speed difference. That is a key point. Getting there faster in calendar time usually means you arrive with a larger leftover speed relative to Saturn, the number engineers call hyperbolic excess. That leftover speed decides how hard you must brake to stay. Now the price tag, stated the way trajectory teams talk to launch vehicle teams. They use C3, short for characteristic energy. Think of it as the square of your excess speed as you depart Earth's gravity, measured in square kilometers per second. 0 means you barely escape Earth. Higher numbers mean you start the interplanetary trip already hot. Raise C3 and trip times can drop by months, sometimes more than a year depending on the window. But there's a bill. For a given rocket, higher C3 cuts the mass you can send. For a given payload, higher C3 demands a larger, more expensive launcher or extra stages and both. This is where "we can do it in 5 years" turns into "we can do it, but the spacecraft has to go on a diet." Arrival geometry is the back end of that same trade. Come in steeper and faster, and the burn to capture into Saturn orbit grows. The capture burn isn't a nice to have, it's the gate to living in the system. If your approach brings you in with a few kilometers per second of excess, your engine has to shave that down while you aim through a safe corridor that avoids ring debris and keeps heating in bounds. Push the arrival speed too high, and the burn becomes too long, too big, or too risky to schedule in one pass. That's when designers start pulling other levers. You shape approach angle to skim the weak upper atmosphere a little for drag if you dare. You target a first loop that threads between the rings to cut risk. You lean on Titan for post-capture gravity assists to reshape the orbit slowly. Or, if you want to cut the burn without shrinking the payload, you look upstream and add gravity assists before you ever get to Saturn. This is why the 6 years number is a floor, not a promise. The ellipse says you can do it that way, but your actual clock is a negotiation between window quality, launch energy, payload mass, and arrival speed. Every knob you twist helps in one place and hurts in another. You can shape calendar by raising departure energy, but your mass drops and your capture burn swells. You can keep the mass and the burn modest, but then you accept a longer cruise or a pickier window. You can try to do both, shorter and heavy, but now you need help from somewhere that isn't your propellant tank. So where does the extra time come from when you want to go faster without throwing away the spacecraft? You borrow it from moving planets. A precise flyby of a big world can hand you speed in the sun's frame without lighting your engine, cutting months or years off the trip while protecting your capture plan. That sounds like cheating, but it's just momentum bookkeeping, and it's the main tool that turned 6 years minimum into 3 to 4 years flyby on the Voyagers, and 6.7 years with an orbiter and a probe on Cassini. The catch, of course, is that the planets have to be in the right places on the right dates with the right angles. Miss those two and you wait, or you pay in energy again. So if you want shorter calendars without starving the payload or exploding the capture burn, who actually pays the bill, and how you line up those planetary handshakes so the speed shows up exactly when you need it? How do you go faster without burning more fuel and still show up on time? You use a gravity assist. And no, the planet doesn't push you like a billiard ball, you trade momentum with it. In the planet's own frame, you come in, curve around, and leave with the same speed, just a new direction. Switch to the sun's frame, and that direction change is everything. You steal a little of the planet's orbital motion and convert it into your speed around the sun. Net result, your heliocentric speed jumps without lighting the engine. The closer you skim, the stronger the bend, but the corridor is tight. Too low and heating, tides, or atmosphere can punish you. Too high and the turn is weak. Navigation teams live on targeting the flyby plane, the miss distance, and the timing to the minute, because a small angle error at the planet becomes weeks of arrival error at Saturn. Now, a concrete play. Cassini's long game. Launched in 1997, Cassini did a Venus-Venus-Jupiter-Earth sequence, a chain people shorthand as VVEJGA. First Venus swing in 1998, second in 1999, back past Earth later in 1999, then the big turn at Jupiter in 2000, and Saturn capture in 2004, a cruise of about 6.7 years. Those assists did 3 things at once. They raised Cassini's energy without huge propellant, they lined up the arrival geometry for a safe orbit insertion, and they kept mass on the spacecraft for instruments and the Huygens Titan probe. The price was operations pain and thermal extremes. Near Venus, the ship baked at roughly plus 130 Celsius. Deep at Saturn, it saw roughly minus 210. All with the same spacecraft, the same blankets, the same radiators. That is the practical face of free speed. You pay with complexity and environment, not fuel. Then the speed run case, the Voyagers. The late 1970s Grand Tour alignment put the outer giant in a row that was too good to waste. Voyager 1 launched in 1977, hit Jupiter in 1979, grabbed a massive boost and crossed Saturn in late 1980, about 3.2 years from Earth to Saturn. Voyager 2 launched earlier in 1977, took a different path and timing, and reached Saturn in 1981, roughly 4.0 years. Both were flybys, no braking, no capture, maximum science in a short, high-speed window, then goodbye. That is what a well-timed Jupiter assist can buy, calendar time that chemical rockets alone struggle to match, especially when you refuse to shrink the spacecraft to nothing. Here's the catch that ruins lazy schedules. Assist windows are picky. If Jupiter is not where you need it on the date your launcher and spacecraft can actually fly, you wait. Not weeks, years. You can try to brute force the miss with higher launch energy, but that means a bigger rocket, a smaller payload, a nastier arrival speed, often all 3. Even inside a good window, the exact day and hour matter, because shaving or adding a few days before a flyby moves the angle at the planet and break your downstream targeting. Teams build backup launch days with new trajectories. They redesign each flyby on the way based on real tracking. They rethread the needle after every tiny statistical nudge. Miss a key assist and the rest of the chain may not exist anymore. So why do we keep doing this even when it complicates everything? Because gravity assists are how you buy calendar time when your launcher can't buy characteristic energy. If your C3 budget is limited but you still want a shorter cruise, you stack assists, you bend the path, and you let the planets pay the speed bill. That is how Cassini arrived with enough mass to work for 13 years, and how the Voyagers hit Saturn on sprint times that still sound aggressive today. The technique scales too. Small probes can run even tighter passes. Large orbiters can mix modest assists with controlled burns to keep arrival speeds in a safe capture range. Done right, you get months to years back on the clock without hauling a skyscraper of propellant. There's a hard ceiling though. Assists don't change what you must do at the end. If you plan to stay, you still face the capture problem. And if you show up hot because you chase time, the insertion burn grows. That is where the trade becomes blunt. Do you keep stacking assists to temper arrival speed? Do you accept a longer trip to make the burn reasonable? Or do you bring a bigger stage and try to muscle through? Mission design is about balancing those knobs so the calendar shrinks, the mass stays believable, and the final maneuver is survivable. Which raises the next sharper question. If assists are the smart way to steal time, what can you realistically do with the chemical rockets you could launch in the near term, without waiting on rare alignments, and how fast can you get to Saturn while still carrying real science and surviving the capture burn? How much time can you actually buy with a big chemical rocket? You pay for departure energy up front, and that number has a name, C3, the characteristic energy. Think of it as how hot you leave Earth. The higher the C3, the shorter the cruise can be, because you start your solar orbit already stretched towards Saturn. Push C3 high enough and you can skip one or more gravity assists. You shave months, maybe a year or two off the cruise. But there's a hard cost. Mass to Saturn falls fast. The same launcher that can send a healthy orbiter on a lower energy path might only send a light probe if you demand the aggressive high C3 shot. Here's what you're aiming for at arrival. When you meet Saturn, you arrive with some leftover speed relative to the planet. Engineers call that hyperbolic excess, or V infinity. For a capture, you want that number in the few kilometers per second range. Not 0, not 10, because the capture burn has to knock it down to bind you to Saturn. Cassini's Saturn Orbit Insertion burned for about 96 minutes and trimmed roughly 626 meters per second, and that was carefully designed to be achievable with the engine, the propellant, and the thermal limits the spacecraft could survive. Many orbiter designs budget something like 0.6 to 1 kilometer per second, with margin, knowing that a hotter arrival pushes that number up and a cooler arrival pulls it down. Now the trade curve, where schedules are born and payloads die. Faster launch means higher C3, which means your launcher can't throw as much mass, so your orbiter gets smaller, your propellant tank shrinks, or your instruments get cut. Faster arrival means you show up with a bigger V infinity, which means your Saturn Orbit Insertion pushes harder, which means a larger capture stage, which again means more mass you had to launch. Push both ends at once and you find yourself demanding a heavy launcher plus a big capture stage while also insisting on a large science payload, and the math stops closing. That's why designers pick a point on the curve, not the extreme. They buy some departure energy, they shape the path with modest assists if the window allows, and they keep the capture burn in a range the spacecraft can actually execute. So what is the realistic time box with the chemical lifters you could book in the near term? For orbiters that plan to stay and do serious science, think roughly 5 to 7 years, depending on how good the alignment is, how much C3 you fund, and how heavy you insist the payload be. You can hit the 5 end with a strong launcher and a lean spacecraft. You drift towards 6 to 7 when you protect payload mass and keep arrival speed saner. For fast flybys where you refuse to brake and you prioritize calendar, 3 to 5 years is credible, again controlled by window quality and how much departure energy you can afford. The low end of that band leans on Jupiter if the timing is kind. The high end works without it but accepts more months in cruise. There is a practical ceiling you can't ignore. Chemical propulsion is great at short, hard pushes. It is not great at carrying both huge fuel loads and huge payloads for outer planet jobs. You can sprint, but you can't sprint with luggage. If you try, you either downsize the science until the mission stops being worth it, or you risk an arrival burn so severe that a single fault turns a decade of work into a dead flyby. That is why the tomorrow-ish answer lives in those time bands, and why anything much faster starts dragging in exotic braking, risky thermal environments, or propulsion that isn't just tanks and pumps. So the next decision is simple to say, Hard to live with. Do you take the quick picture and leave? Do you pay the arrival tax and move in? Or do you aim for Titan and add a probe on top of everything else? And how does each choice push the clock in different ways? What exactly are you trying to do at Saturn? Blast past, settle in, or drop hardware into Titan's sky? That single choice sets your clock more than any headline speed number, because each mission type changes how much energy you spend, how much mass you can carry, and what you must do at arrival. Start with the sprinter, the flyby. You do not brake, you do not spiral down, you shape a path that threads the target at high speed, collect a flood of data, and keep going. That's why flybys can hit Saturn in roughly 3 to 4 years when the Jupiter assist lines up, like the Voyagers did. You use the launch to get moving, you let Jupiter hand you a big speed boost in the sun's frame, and you arrive at Saturn with a high relative velocity that you never try to cancel. The upside is obvious: calendar speed, minimal propellant for arrival, a simpler spacecraft compared to an orbiter. The costs are also clear. Your encounter is hours to days at useful range. Your lighting and geometry are whatever the date gives you, and there's no do-over. Miss a ring plane pass by a little or get unlucky with pointing, and that opportunity is gone forever because you're already outbound. Now the renter, the orbiter. This is the choice if you want seasons of data, repeated passes through ring arcs, dozens of flybys of moons like Titan and Enceladus, and long baselines for weather and magnetosphere. The price is a capture burn and months of trajectory tailoring. You arrive with a few kilometers per second of leftover speed relative to Saturn, and you must take a chunk off that with your engine during Saturn Orbit Insertion. Cassini's insertion burn lasted about an hour and a half and removed roughly 626 meters per second of speed. That maneuver turned a flyby into a decade of science. After capture, you still spend weeks to months reshaping the orbit, raising or lowering closest approach, rotating the orbital plane, threading safe ring plane crossings, and timing Titan flybys to pump the orbit into the geometries you need. All of that adds calendar. That is why the realistic number for a chemical orbiter is about 6 to 7 years cruise, depending on the window and how hot you allow the arrival to be. Then the special case that bends schedules further: probe delivery to Titan. Titan is cold, around minus 179 degrees Celsius at the surface, wrapped in a dense nitrogen atmosphere with a haze that blocks most visible light. That thick air is perfect for a parachute entry probe like Huygens, but it locks your arrival geometry. You need the mothership to deliver the probe onto a narrow corridor that hits Titan's upper atmosphere at the right speed and angle, at the right local time, and with a radio link for relay if you want live data. That constrains your approach path and your timing. If your orbital mechanics say the easiest arrival is wrong for Titan entry, you either wait for a different alignment, add corrective maneuvers that cost fuel and time, or accept less than ideal comms and lighting. Every one of those choices can nudge the cruise length in the early months in system. There's also ring science timing, which many viewers underestimate. The rings are not just pretty, they are a dynamic system where lighting angle changes the data you can get. Near equinox, when the sun grazes the ring plane, the rings are backlit, vertical structures pop, and faint features stand out. Near solstice, when the sun hits at a steeper angle, you read composition and scattering differently. If your top-line science needs equinox lighting, you don't want to arrive years too early and wait. You bias your window so that your prime sequences line up with that season. That can force a later arrival or a longer cruise if the good energy window and the good ring season don't coincide. Mission teams will often trade several months of extra travel to land the science in the sweet spot, because those seasons only come around on Saturn's long year. Put the 3 mission types side by side and the clock logic is blunt. Flyby is the fastest, about 3 to 4 years when you catch the right assists, because you refuse to pay the braking bill. Orbiter is the worker, about 6 to 7 years with today's chemical stacks, because you accept the arrival tax and you add months of careful orbit trimming for safety and science. Titan drop rides on top of either plan but narrows the corridor. It can stretch timelines or add constraints that ripple back into your launch window and your early in-system operations. None of this is hand-waving. It's the direct result of how much speed you shed at arrival and how much geometry you must control after capture. The bottom line is not a slogan, it's a rule. How long starts with what science. If your goal is a fast postcard and a clean exit, you can move quickly and travel light. If your goal is long-form science, rings, weather, geysers, magnetosphere, you plan for the capture burn. You guard margins and you accept a 6 to 7 year cruise. If your goal is to drop a probe through Titan's atmosphere, you take on a stricter arrival corridor and tighter timing. Speed always costs flexibility. If you try to keep speed and keep flexibility and keep mass, the math pushes back and the risk at arrival goes up. So if the mission type locks the schedule this hard, is there any way to buy back a year or two without throwing away your payload? Can you pay in raw launch energy instead, skip assists and still survive the arrival burn? How much time can you buy by paying pure launch energy? No planetary help, just a hard shove off the pad. With a no-assist high C3 trajectory, you leave Earth already hot. Your solar path stretched towards Saturn from day one. Do that, and an orbiter can come down into the roughly 4.5 to 5.5 year band, while a flyby can land in about 3 to 4 years, even without a Jupiter slingshot. The calendar drops because you're not waiting to meet other planets. You're not choreographing mid-course bends. You depart, you cruise, you arrive. Simple on paper, but every month you shave comes straight out of the mass you can deliver. Here's the mass cliff, and it is brutal. For a given rocket, each notch of characteristic energy slashes what you can throw to the target, and the penalty grows faster than you expect. Push C3 a little, payload trims. Push it hard, payload collapses. This is where a credible flagship orbiter starts turning into a stripped bus, then into a small probe with a big antenna. You can upsize the launcher or add an upper stage, but that bill shows up in dollars, risk, integration time, and fairing limits. Mission reviews get very tense here because the calendar looks great until you see the instrument list you can no longer carry. Fast arcs also hit you on environment and communications. Leaving hot usually means a steeper solar angle early, more sunlight on your hardware, tighter thermal margins, and shorter time to cool down after Earth departure. Later, during the long middle of cruise, you're farther, sooner, so your link to the deep space network is weaker for longer. That means bigger antennas, more transmitter power, stricter duty cycles, and ruthless data budgets. Or you accept blackouts during parts of cruise. The ops team now has to schedule tracking passes with less margin, and your navigation covariance balloons faster if you miss coverage. All of this is solvable, but it's not free, and it eats the mass you thought you saved. Arrival brings the hardest reality check. Show up hot and your arrival speed relative to the planet is larger. If you want to capture, your engine must remove that extra speed in the insertion burn. That means a bigger propellant load, a bigger tank, a larger engine, or more time in a hazardous corridor near the rings while the burn runs. There's no free lunch here. If you don't carry the fuel, you don't capture. If you carry the fuel, you probably gave up instruments to make room. If you try to split the difference, you risk a burn that pushes your thermal or pointing limits while ring plane debris lurks one guidance error away. A fast calendar is great, right up until the last 90 minutes, when the mission lives or dies on thrust and timing. So who actually benefits from paying cash for time? Compact probes and tech demos. If your payload is small, your power needs are modest, and you can live with a short encounter or a lean capture, high C3 direct shots shine. You get a clean operations profile, fewer interplanetary events to fail, and a quick arrival that showcases new hardware. For a heavyweight orbiter, the picture is harsher. You either undercut the science by shedding mass, or you arrive too hot and spend everything you saved on a giant braking stage. That is why direct, high-energy arcs tend to be a niche choice for flagships, a mainstream choice for scouts. There's a middle path some teams take. You buy a moderate C3 bump to cut months, you keep one well-placed interplanet assist to hold the payload line, and you manage arrival speed so the insertion burn stays in a sane range. It's not as clean as no assists, and it's not as fast as the most aggressive plan, but it closes the books with fewer red flags. The lesson is blunt. Chemistry can sprint, but it can't sprint with luggage. If you try to keep the big payload, the short cruise, and the safe capture all at once, the numbers fight you. To break that deadlock, you either accept assists and calendar, or you change the game entirely and make your burn count where it matters most down, deep in the sun's gravity well, where the same kilogram of propellant buys you far more speed. How far can you bend time if you dive toward the sun and hit the throttle at the last possible moment? And what does it take to keep a spacecraft alive that close to that much heat? Want the biggest speed boost for the same fuel? Spend it where gravity makes it count most, deep near the sun. The move is simple to say, hard to fly. You dive inward on a sundiver path, swing past the sun at a blistering perihelion, and fire the engine right there. Because you're in the strongest part of the gravity well, each kilogram of propellant buys more speed than it would out near Earth. You leave that burn carrying extra heliocentric energy, and when you climb back out towards Saturn, you're on a much faster trajectory than a normal transfer could touch. How much faster can that be in real numbers you can use? With perihelion passes only a few solar radii above the surface, a well-timed burn can add tens of kilometers per second of excess speed relative to the sun. That is not a rounding error. That is years off the calendar. A cruise that looks like 6 or 7 years on a conservative plan can compress toward the low single digits for certain profiles. The catch sits right next to the prize. At those distances, sunlight is brutal and heating rises very fast as you move inward. Miss your shield margins and the vehicle doesn't run hot, it fails. Survive it and you come out with a speed you can never afford from launch energy alone. We do have proof that this neighborhood is reachable. Parker's solar probe has already flown repeated, extremely close passes and set heliocentric speed records, showing that hardware can operate at distances that used to sound theoretical. That doesn't mean a Saturn orbiter can just copy the play. Parker is a lean, heat shield forward design with a very specific mission. An orbiter for Saturn needs a heavy capture system, big antennas, power, propellant management, and a thermal design that works both near the sun and in deep cold later. Surviving the sun dive with that mass and shape, then lighting a main engine right at perihelion on a tight timeline is a different class of challenge. The engineering gates are unforgiving. First, shield mass and materials. You need a heat shield that protects not just the bus, but also tanks, plumbing, and guidance sensors, and that shield can't be so heavy it kills your mass budget. Second, guidance accuracy at perihelion. The burn happens fast, the gravity turn is sharp, and any pointing error wastes delta V and slashes the benefit you came for. Third, staging choreography. If you carry a dedicated Oberth stage, you must ignite, burn, and separate on the clock, while the vehicle is under extreme thermal load and high angular rates. Fourth, system survivability and ops. Avionics must stay cool enough to compute and steer. Valves must open on cue. Prop lines must not cavitate, and your attitude control has to manage plume torques and shield pointing without glitching. You also plan for comms blackouts near the sun and rely on autonomy. That raises the bar on software and fault management. Even if you nail the dive and the burn, arrival still has the last word. You will reach Saturn hotter than a conventional plan, which is the whole point. But now capture is harder. If you want to stop, you either bring a larger braking stage, accept an aerocapture risk that nobody has flown at a giant planet yet, or you resign yourself to a flyby. This is why sundiver profiles are most attractive for probes that don't need to stay, or for tech demos that can accept a lean payload. For a flagship orbiter with a decade of science on the line, the added speed must be weighed against a bigger, riskier insertion maneuver at the end. So what is the realistic verdict, stripped of hype? A solar Oberth maneuver can plausibly pull a Saturn flyby down into the 2 to 3 year class if you build for heat, nail guidance, and keep the spacecraft compact. That is a serious schedule cut. But for an orbiter, capture still looms. You can arrive faster, yes, yet you must either bring the propellant to brake or invent a different way to slow down. If the arrival plan doesn't close, the calendar win doesn't matter. Teams that pursue this route usually pair the sun dive with careful arrival shaping or with a post-arrival moon tour that trades time for fuel once you're bound to Saturn. This leaves a clear fork. If the goal is speed above all and a flyby is acceptable, the sun will sell you time at a steep but manageable engineering price. If the goal is to live at Saturn, the sun helps you leave Earth faster, but it does not cancel the arrival bill. Which raises the next question you have to answer honestly. If you want shorter calendars and you still need to capture, can you swap propellant for efficiency by thrusting for months instead of minutes? And is there a propulsion system that makes that trade practical without giant solar panels that die at 9 9.5 astronomical units. Can you trade short, violent burns for a steady push and win back time without hauling a giant fuel tank? That's the electric play. Instead of blasting for minutes, you thrust for months, even years, sipping propellant and stacking velocity a little every day. We've already proved the core idea works. NASA's Dawn mission used ion engines with very high efficiency, a specific impulse around 3,100 seconds, and racked up roughly 11 kilometers per second of total speed change. Dawn orbited Vesta, left it, and then orbited Ceres, all on electric thrust. It worked because the spacecraft lived where sunlight still delivers usable power, roughly 2 to 3 astronomical units from the sun, and because the payload and operations plan were built around long, continuous burns. Move that concept to Saturn and you hit the power wall fast. At Saturn's distance, the sunlight is about 1/90th of what it is near Earth. Solar electric propulsion that feels reasonable in the inner solar system collapses out there. To get the same kilowatts for your thrusters near Saturn, your solar arrays would need to be enormous, heavy, and fragile, with deployment and pointing complexity that dominates the spacecraft. Even if you accept giant arrays, the thrust at 9 to 10 AU is tiny, so tiny that trajectory shaping slows down just when you most want control for arrival. You can keep the panels modest and do most of your thrusting inside of, say, 3 AU, then coast, but that pushes you back toward the same 6-ish times you were trying to beat, and it leaves you with less authority to trim arrival speed. For a serious orbiter, SEP is a poor fit at Saturn distances with today's arrays. Enter nuclear electric propulsion, the version that doesn't care how dark it is. Swap panels for a compact reactor, feed hundreds of kilowatts to about a megawatt into high-efficiency thrusters, and you unlock a different game. With steady power, you accelerate for months after Earth escape, bend the path without assists, and then, crucially, you can flip the thrust vector late in cruise to bleed off arrival speed before you hit Saturn's sphere of influence. Do that well, and you can compress an orbiter's time of flight towards something like 3 to 5 years, shaving a year or more off a conventional baseline. And you can arrive with a smaller capture burn because your V-infinity is lower. That is the promise. Faster outbound, finer control near arrival, and less dependence on narrow planetary alignments. But none of that is free. A megawatt-class space reactor is not just a box. It is core, shielding, power conversion, radiators, structures, and fault tolerance. Waste heat must be rejected, and at these power levels, radiator area gets large quickly. You also need a propellant supply, typically xenon, at tens of tons if you want serious total delta V. Big tanks, feed systems, and pressure management are now major design items. Thruster lifetime matters too. Ion and Hall thrusters wear slowly but steadily, so a multi-year burn profile pushes you into modular arrays, hot spares, throttling strategies, and erosion budgets that must close. Every piece has to work together for thousands of hours. If any link in that chain underperforms, your trajectory margin shrinks. Operations get more demanding, not less. Low thrust means your path is never a clean conic section. It evolves continuously. Navigation must account for tiny errors that integrate over months. Autonomy has to be stronger because you're thrusting during long communication gaps, and the guidance software has to recompute thrust vectors on the fly when tracking updates arrive. Fault budgets get tight. A week-long thruster outage doesn't strand you, but it shifts your arrival state by millions of kilometers unless you compensate. The upside is precision. With persistent thrust, you can shape the arrival to thread ring plane crossings, time Titan flybys, and target capture conditions in ways a one-shot chemical burn can't match. Window discipline changes too. With steady acceleration, you're less hostage to one perfect departure date. You can launch in a broader season and use thrust to fix phasing as you go. That buys schedule flexibility. It doesn't erase geometry though. Saturn still has to be where your faster path will meet it, and if you want a Titan delivery or a specific ring season, you still align to those deadlines. The difference is that you have more knobs to turn during cruise, so you can correct earlier and cheaper than a pure coasting trajectory allows. Bottom line, stripped of hype, solar electric propulsion is excellent inside the asteroid belt, but at Saturn it runs out of light. You can use SEP to get moving fast while you're still close to the sun, then coast. but the calendar gains are modest and the arrival control is weaker. Nuclear electric propulsion, at roughly a megawatt with mature radiators and robust thrusters, changes the picture. You keep the high efficiency, you keep thrusting in the dark, you beat Hohmann by years, and you show up with a gentler capture. The risks shift from propellant mass to power and thermal systems, and the entire mission hangs on power plant reliability and long-life thrusters. So if electric can cut time with constant push but asks you to build a flying power plant, is there a nearer-term way to buy speed with simpler hardware? What happens if you keep chemical simplicity but double the efficiency of the engine itself? And can hot hydrogen move the schedule into the 3-year band without the reactor baggage? Go faster by burning less. That's the promise of nuclear thermal rockets. Instead of making hot gas with chemistry, you run liquid hydrogen through a compact reactor, heat it to extreme temperatures, and throw it out the nozzle. The exhaust is faster, the efficiency jumps, and the same tank of propellant buys you a lot more speed. In simple terms, you double the specific impulse versus typical chemical stages, from a few hundred seconds to something near 900 seconds. So for the same total speed change, you need roughly half the propellant. Or for the same propellant, you can aim for a much quicker trip. That single upgrade changes the calendar in a way you can feel. Here's what that means for a Saturn run. With an NTR upper stage doing the heavy lifting after Earth escape, you can buy a hotter departure without killing your payload, then keep margin to trim arrival speed so capture stays sane. You're not chasing miracles here, you're just spending delta V more efficiently across the whole flight. On paper, and in many design studies, an orbiter lands in something like the 2.5 to 4-year band without exotic solar dives, assuming a solid launch window and competent staging. You either use the higher efficiency to leave sooner and coast faster, or you use it to keep thrust authority late in cruise and arrive cooler, which shrinks the Saturn Orbit Insertion burn. Both approaches move you off the 6 to 7-year chemical baseline. The architecture is straightforward to describe. A heavy lift launcher places a spacecraft and an NTR stage in Earth orbit. The reactor lights for the interplanetary push, then shuts down. Weeks or months later, you restart for cleanup burns, trajectory tweaks, and, if you plan it that way, a long shaping burn that lowers your leftover speed relative to Saturn before you enter its sphere of influence. Restarts matter because this isn't a single 90-minute event. It's multiple long burns across the mission. The gain is flexibility. You can burn when it helps most, not just when your tanks and engine chemistry allow. Now, the trades that keep engineers honest. Hydrogen is the perfect propellant for NTR because it gets so light and fast when heated, but it's also hard to store. It's cryogenic, it leaks through seals, it wants to boil away, and it takes a lot of volume for the mass you need. If you expect months to years of storage, you need excellent insulation and ideally active refrigeration to hold losses near zero. That means power, radiators, controllers, and mass. You also need a tank arrangement that handles slosh and keeps feed lines cold and stable across long coasts and repeated burns. Every kilogram you add to make storage reliable is a kilogram you aren't sending to science. But skipping that hardware risks arriving with less propellant than the math assumed. Reactor safety and operations are another gate. You must prove the core can start, run hot, and shut down safely, then start again, many times, with stable thrust and no material damage. The few elements inside the reactor face intense temperatures and hydrogen flow that can erode surfaces. You need materials that hold up across the full profile. You also need shielding to keep doses acceptable for avionics, for any nearby payloads, and in a crude case, for people. Shielding costs mass, and you place it to shadow critical systems while allowing tanks and radiators the line of sight they require. Thrust vector control and nozzle cooling must survive long burns without drift. None of this breaks physics, but it sets real requirements that determine whether you actually get the calendar the trajectory promised. Why does this matter so much? Because time is not just a convenience at Saturn, it's a mission enabler. For crewed missions, shorter transit means lower radiation dose, fewer months of life support, less consumables mass, and simpler countermeasures for bone and muscle loss. For robotic missions with narrow science windows, rink seasons, equinox geometries, plume activity cycles. Getting there in 2 to 4 years can be the difference between hitting the prime geometry and missing it by an entire Saturnian season. NTR is the near-term lever that moves your really from 6-ish years toward 3 using technology that extends existing rocketry rather than inventing a full space power plant. Keep the caveats in view. Arrival still rules the endgame. If you sprint and show up hot, you must brake. NTR helps by letting you carry a meaningful capture stage without destroying payload mass, or by letting you spend part of that high efficiency late in cruise to reduce your approach speed before Saturn Orbit Insertion. You can also thread gentler approaches, higher first orbits, longer periods, planned moon flybys to take bites out of capture over weeks instead of one brutal burn. The engine buys options. It does not cancel the physics of binding yourself to a giant planet. There are practical limits. You still need a launcher that can lift the stage and the spacecraft. You still need thermal control that works both warm near the sun and bitter cold near Saturn. You still need navigation and guidance that handle long burns without drift. And you still need margins for the failure that shows up on the worst day, at the worst time, when the insertion burn is running and the ring plane is close. The reason NTR is compelling is that it moves several of those limits at once. Less propellant for the same job, more delta V for the same mass, more control over when you spend it. The reason it isn't automatic is that hydrogen storage and reactor ops are hard, and you don't get infinite tries at Saturn capture. So you've got a faster engine and a shorter cruise, but you still owe a big speed payment at the door. If propellant is precious and time is tight, can you swap flame for drag and let the destination do the braking for you, trading fuel mass for heat and precision in a single pass through a dangerous atmosphere? How do you stop without firing the engine? You use the atmosphere as your brake. Aerocapture is the direct version of that idea. Instead of spending a huge capture burn to slow down at Saturn, you aim the spacecraft to skim through the upper atmosphere, Saturn's or Titan's, let drag shave off the excess speed, then you pop out already bound to the planet. No propulsive capture, one pass, then optional cleanup burns later. If you stretch the same method across many gentle dips, that's aerobraking. Here, we're talking about the single hard pass that replaces hundreds of meters per second, sometimes more than a kilometer per second of engine work with controlled heating and drag. What's the payoff in plane terms? Freedom to arrive faster and heavier. If your heat shield and guidance can handle it, you can tolerate a higher arrival speed, the V infinity you carry into the system, and still end up in orbit. That lets you choose shorter interplanetary arcs, the kind you'd normally reject because the capture burn would be too big. Every meter per second you remove with air is a meter per second you don't have to carry in propellant. Depending on design, that can save hundreds of meters per second, sometimes more than 1 kilometer per second of chemical delta V. That's a lot of mass back in your pocket for instruments, power, comms, or simply for margin you'll be glad you kept. Where's the risk? Everywhere your models are weakest. No one has ever aerocaptured at a giant planet. We've aerobraked at Mars and skimmed Venus, but hydrogen helium giants are a different regime. Saturn's upper atmosphere is thin but dynamic. Density can change with latitude, local time, and weather. Go too shallow and you skip out. Still hyperbolic, mission lost. Go too deep and heating spikes, loads rise, and you can damage the vehicle in seconds. The path you aim for is a narrow corridor of acceptable dynamic pressure and heat rate, and you hold yourself in it by banking the aeroshell to control lift. Small guidance errors can push you above or below that corridor. Add the ring system to the picture, and the approach geometry must also keep you clear of dust and debris during approach and immediately after you exit the atmosphere. The corridor is narrow, and the consequences for missing it are unforgiving. The hardware is not a simple add-on. You need a heat shield sized for giant planet entry speeds and long enough exposure to bleed the speed you planned. That shield must protect tanks, lines, ionics, and sensors, not just the forward bulkhead. You need a structure with the right ballistic coefficient, mass per area, so the vehicle bites the air predictably. You need control authority to bank and hold attitude while plasma flows and accelerometer spike. And you need thermal paths to carry heat away without cooking critical components. And you need autonomy because you won't be joystick flying a periapsis over 1 billion kilometers away with a round-trip light time approaching an hour and a half. The vehicle must sense, decide, and steer on its own through the hottest minute of its life. What about Titan instead of Saturn? Titan's thick nitrogen atmosphere is attractive. Heating is friendlier than a Saturn main body dip, and the environment is well suited for parachutes and lifting bodies. Huygens proved entry, descent, and landing in 2005. But Titan aerocapture is not easy mode. The arrival corridor is still tight because you must hit the right altitude and speed to get enough drag without burning too much time or risking breakup. Geometry bites here too. You need the mothership's trajectory set so you can deliver the probe and still end up on a useful orbit afterward, with workable lighting and a comms link for relay if required. That narrows your launch windows and arrival dates. It solves some problems and creates others. Does aerocapture change the calendar by itself? Not directly. Cruise time is set by your interplanetary trajectory. What aerocapture does is unlock faster trajectories by making the hot arrival survivable. If you're willing to take a higher V infinity and trust the heat shield, guidance, and structure to bleed it off in atmosphere, you can pick a shorter path and still become an orbiter at the end. Post-capture, you may still need weeks to months of aero braking or small burns to shape the final science orbit, but you've already paid off the largest speed debt without a giant propellant bill. In that sense, aerocapture is a financial tool. It lets you spend heat instead of fuel to afford a faster schedule. So why hasn't anyone done it at a giant planet? Because the margins are thin, the uncertainties are real, and the cost of a miss is the mission. Density noddles must be good enough to set the corridor. Guidance must hit the corridor and stay in it. The shield must take the heat and survive with margin. The navigation leading into periapsis must be precise, since a tiny error in angle or altitude becomes a huge change in peak heating. And all of this happens at the end of a multi-year cruise, when you only get one try. Teams tend to stay conservative when a decade of work is on the line. Still, the upside is compelling. If you can prove the models, fly a shield that holds, and validate the guidance in flight earlier in the mission, aerocapture can turn a heavy, capable orbiter into a faster arriving mission without starving the payload. It can also pair with gravity assists or modest nuclear thermal staging. Arrive hotter than a chemical-only plan, let the air take the big bite, then spend smaller burns to clean up. The technique is not magic. It's a high-risk way to move mass from tanks into thermal protection and software, and in the right design, it makes the clock bend. Here's the hard pivot. If aerocapture helps hardware arrive fast and heavy, what happens when the payload is people? Time stops being just a schedule win and becomes a life support and radiation number. How short do you need to make the legs before dose, consumables, and psychology say do it? And which propulsion choices actually make that possible without turning the risk dial to maximum? How fast is fast enough when the payload is people? The clock stops being a schedule preference and becomes a medical number. Outside Earth's magnetic shield, you sit under a steady drizzle of galactic cosmic rays, and sometimes a blast from a solar storm. Dose accumulates day by day, and there is no pause button. Shave months, you cut dose. Shave years, you change outcomes. You still bring a storm shelter, you still line crew quarters with water or polyethylene, you still manage solar event alerts, but the cleanest lever is time in transit. Less time in deep space, less hadronic punishment. Fewer days where a surprise flare can stack dose on top of baseline. The next pressure is mass, and it ramps fast. Every extra month adds water, food, oxygen reserves, CO2 scrubber consumables, spares, and redundancy. The longer the flight, the more you need margin for system failures, so you duplicate pumps, fans, valves, avionics, and you carry repair kits for the things you can't duplicate. You pack medical supplies for more contingencies. All of that rides against your launcher. Stretch a mission from 3 years total to 5, and your life support mass and spares plan can explode past what a single heavy lift can throw, forcing multiple launches, assembly, or on-orbit refueling, each one a new risk and a new cost center. Shorter legs also change how you handle gravity. Without spin gravity, crews lose bone and muscle, and fluid shifts wreck sleep and vision. So you either build an artificial gravity system, tethers, rotation booms, bearings, controls, or you run daily countermeasure workouts with strict discipline. If you compress the crews, you can relax the need for a large rotating structure, which simplifies the vehicle and cuts mass. You still exercise, you still medicate where needed, but you're not asking bodies to adapt for half a decade. That reduction in complexity feeds back into the risk ledger and the launch mass tally. Operations and psychology improve when the calendar shrinks. Communication delays in the Saturn neighborhood are harsh, on the order of 70 to 90 minutes one way, depending on geometry. So round-trip guidance is hours, not minutes. With a shorter mission, you cut the months spent working around that delay in deep space. You reduce periods where ground can't help you quickly, and you shrink the window for rare but mission-ending anomalies. Schedules stay tighter, crews stay focused, and fatigue from endless cruise ops doesn't have years to accumulate. You still train for autonomy, you still practice failure management, but you aren't asking a team to ride a 5-year attention marathon. Put the drivers together and the target emerges. A credible crewed Saturn mission wants sub-3-year legs, outbound and, if you return, inbound in the same class. That number isn't a brag. It's where dose, consumables, reliability, and human performance start to look manageable without heroic mass or exotic shielding. Hitting that bar forces propulsion beyond pure chemical. You're in nuclear thermal or nuclear electric territory, possibly with a small Oberth assist if the heat shield and ops risk can be contained, and you're hunting aggressive windows that reduce phasing losses. You also lean on precision navigation to trim energy before you touch Saturn's sphere of influence, because a crewed capture burn must be large, reliable, and short, not marginal. This choice cascades into architecture. With NTR, you cut propellant mass for the same delta V, which keeps the habitat and shield incredible while still buying a hot departure and a cooled-off arrival. With NEP, you throttle continuously, building speed in the inner system and bleeding it late, turning a single terrifying insertion into a smaller propulsive event. Either way, you keep a storm shelter, you design your radiation plan around worst-case solar events, and you accept that crew health pushes you towards shorter, more decisive burns and fewer delicate flyby chains. Aerocapture at Saturn for crew is a tall order today. Uncertainty margins are thin, but a Titan aerocapture for a cargo vehicle that prepositions supplies and propellant is not out of the question, and it can de-risk the cruise ship's capture by offloading mass. Crew count matters too. Fewer people lower consumables and shielding mass, but increase workload and fault vulnerability. More people add redundancy and onboard repair capability, but drive the mass back up. Life support reliability is the other wall. A 2.5-year leg demands hardware you can service in flight, with graceful degradation, hot spares, and simple, well-documented procedures. Shorter doesn't mean easier, it means the envelope is tight enough to manage with hardware you can realistically test and certify. Here is the blunt summary. For people, time is dose, time is mass, time is complexity. Cut time and everything else starts to work. Keep it long and the stacks of shielding, spares, and redundancy make the rocket small or the bill impossible. That is why propulsion choice is the first decision, not the last. If you cannot field NTR or NEP class performance, your schedule stretches, your mass explodes, and the mission safety case erodes. But propulsion isn't the only clock in play. Even with the right engine, you only get the good routes when the solar system gives them to you. How often do the real windows open? What happens to your plan if Jupiter's not in the right place? And how do Saturn's own seasons twist your arrival date into a science win or a bust? How do you pick a date that doesn't waste years? Start with the basic rhythm. Earth and Saturn form usable lineups roughly once every 378 days. That's the synodic period, and it gives you about annual chances to depart. But those windows are not equal. Some open wide, with lower energy to reach Saturn and reasonable arrival speeds. Others are narrow and expensive, forcing higher launch energy just to hit the same geometry. Trajectory teams map entire seasons of options around each window, because the exact day inside that month-scale band can move your fuel demand by hundreds of meters per second and your arrival date by months. Now layer in Jupiter. If you want a real slingshot, you're no longer targeting the next Saturn window, you're aiming at a chain. Earth to Jupiter, Jupiter to Saturn. That means you care about Jupiter's phase relative to both Earth and Saturn, and those alignments roll through on multi-year cycles. Miss the right year or even the right few weeks, and you don't just pay a little extra energy, you punt the mission to the next cycle. This is why flyby sprints like the Voyagers were tied to rare Grand Tour phasing, and why modern missions that want Jupiter's speed boost plan years ahead with backup trajectories pre-computed for slips. If Jupiter isn't usefully placed, your options collapse to a higher energy direct shot or a longer cruise with different assists. Your science season can dominate just as much as the planet lineup. Saturn takes about 29.5 Earth years to go around the Sun, and its ring lighting flips across that long year. Around equinox, the Sun shines edge-on to the rings and faint vertical features pop. Around solstice, sunlight strikes them at a steep angle, which is better for other measurements. Cassini rode this arc: arrival in 2004, prime mission through 2008, equinox mission across 2009, then a solstice geometry in the later years, all because certain observations only existed on those dates. If you care about equinox physics or high-incidence scattering, you may deliberately choose a later launch to hit the right season, even if a cheaper window exists sooner. There's a safety calendar hidden inside all this. Shorter trips often arrive hotter, which can steer you into ring plane crossings near equinox. Those crossings are gold for ring dynamics, but they raise the dust hazard right where you're busiest with capture burns and trajectory corrections. If your plan calls for threading gaps between the main ring sets, you time your approach to minimize debris risk, and you bias your periapsis to stay away from dusty arcs. Stretching the cruise to reach a friendlier arrival season can remove a mission-ending hazard for minimal added time. Rushing in can trade months saved for a single catastrophic pass through a dusty plane. Operations cadence rides the same wave. A strong window tightens launch schedules, pad availability, tracking assets, and integration milestones. If you slip out of the high-quality day and into a weaker one, your launch energy rises, your payload margin drops, and your arrival speed grows. That single slip cascades into capture risk and early orbit work. Teams therefore build tiered plans: primary dates with best energy, secondary dates with acceptable penalties, and fallbacks that change assist strategy entirely. The goal is not just launch this year, it's launch on a date that keeps arrival survivable and science on season. Budget plays a quiet but final role. A lower energy window can let you use a smaller launcher or carry a larger payload on the same launcher. A higher energy window can demand a bigger rocket or an extra upper stage, shifting millions of dollars and months of manufacturing and test. When finance locks a vehicle and a mass target, some windows simply fall off the table. The mission then flows to the best remaining date that closes both the energy math and the money math. Put it together and the rule is clear. Your mission clock is not only the travel time printed on the trajectory, it's the choreography of 3 moving worlds, the science season you must hit to make the data worth the trip, and your tolerance for energy and risk at arrival. The best window is the one that lands you on the right calendar with a capture you can survive and a payload that still exists after all the trades. Miss that and you either wait a year or more, or you pay with mass and hazard. Which brings you to the next constraint you can't wish away. Even if the dates line up and the energy works, the destination has rules. The rings, the atmosphere, the magnetosphere, the dust, they dictate how you approach, where you burn, and how long early operations take after you arrived. You think arrival means you're done, but the environment decides what arrived really means. First hurdle, the ring plane. If your approach geometry is tight, you can thread a clean gap and cut risk, but that takes exact timing and careful shielding. Cassini's capture flight path crossed the ring plane in a safer lane between the F and G rings during its insertion, using attitude and shielding margins to ride through dust, then fired for the big burn. That level of precision is not optional. A small navigation error alters altitude at crossing, dust density spikes, and the probabilities flip on you fast. Teams often aim for ring plane crossings at longitudes and latitudes with better dust models, accept the slightly longer first orbit, and adjust later with moon flybys. You give up weeks, you reduce the chance a micrometeoroid takes out a radiator or a star tracker. Now the atmosphere. Saturn's upper layers are thin, but they are not uniform. Density varies with latitude, time, and weather, and your predictions have error bars you can't shrink to zero. If you're planning aerocapture or even shallow aerobraking passes, that uncertainty turns margins into cliffs. Too high and you barely touch the air, you fail to dump the speed you budgeted, and you miss the orbit you promised. Too low and heating and loads jump, sensors saturate, and you risk structural damage in seconds. Because round-trip light time is close to an hour and a half, you won't be hand-flying corrections. Banking strategies, lift-to-drag tuning, and autonomy decide if you stay inside the safe corridor. Conservative missions will often replace a one-pass aerocapture with multiple lighter aerobraking dips over weeks, sacrificing calendar to buy down thermal risk. Radiation is next. Saturn's belts are milder than Jupiter's, but they still shape lifetime and operations. Sensitive avionics need shielding and placement in lower-dose, shadowed regions of the spacecraft. You schedule ring plane crossings, high-inclination passes, and close moon flybys with radiation budgets in mind, balancing science value against cumulative dose. Detector noise rises as dose climbs, latch-ups become more likely, and thermal cycles combine with radiation aging to stress parts near end of life. You rotate instruments, manage duty cycles, and build in safe mode logic that doesn't overreact to single event upsets but still protects the bus. The moons give you tools that change everything after capture, especially Titan. Titan's mass and thick atmosphere make it the lever arm for the whole system. A single precisely timed Titan flyby can raise or lower your orbit size, crank your inclination, and rotate your orbital plane, all for trivial propellant. The trade is time. Each gravity assist costs days to weeks, and sequences of assists stretch into months. Cassini's tour worked because it embraced that, using Titan to retarget again and again, turning what would have been large chemical burns into patient orbital sculpting. Smaller moons like Rhea, Dione, and Tethys offer fine-tuning, but Titan is the workhorse. You plan a chain, you watch tracking residuals, and you update targeting every pass. It's slow, it's methodical, it preserves fuel. Debris and dust management never turns off. Even in clean lanes, small particles can pit optics and solar arrays or contaminate thermal surfaces. That's why you see ring plane crossings executed with the high-gain antenna pointed forward as a shield, why non-essential components get powered down, and why you accept awkward attitudes that protect radiators and instruments during the riskiest minutes. Afterward, you run health checks, you recalibrate sensors, and you update your dust models with real data to improve the next pass. Each safe crossing you bank adds confidence and opens up tighter geometry later, but you earn that option. You don't assume it on day one. Operations cadence inherits all of this. The first months after capture are dominated by safety passes, plane changes, instrument checkouts, and ring plane alignments. You schedule periods of conservative flight to validate models, then expand the envelope step by step. Want a polar ring view, or a grazing pass over a narrow ringlet, or a low-altitude Titan approach for radar mapping? You build a ladder of orbits that gets you there without putting the spacecraft in a thermal or debris corner it can't exit. That ladder takes time. When budgets are tight, teams are tempted to compress the early tour. The environment punishes that. Going slow at the beginning often saves you schedule later because you avoid unplanned safing events, sensor damage, or a trajectory redesign that costs months. Even simple sounding activities take longer in this neighborhood. Communications windows depend on geometry with Earth, on DSN allocations, and on when you can safely point the antenna without exposing sensitive surfaces during dusty segments. Downlink rates drop as range rises, so large datasets from close passes may trickle back over days. Navigation solutions depend on star tracker performance, which can be degraded by glare or dust hits during certain attitudes. Each of these realities adds small delays that pile up across a long tour. Put the pieces together and the message is clear. Saturn's environment isn't just scenery, it's a set of rules that adds weeks and months post-arrival before you reach your prime science tempo. If you planned a tight calendar, these rules stretch it. If you plan generous fuel and conservative passes, these rules turn that margin into mission length and data quality. The smart play is to accept that arrival day is the start of a careful ramp, not the beginning of instant hero shots. So when you ask, if we launched this decade with real hardware and today's engineering tolerances, what would the actual timelines look like for a conservative orbiter, a fast flyby, a high-energy direct shot, an NTR-boosted craft, or a solar Oberth probe, and how do those choices stack next to each other on a single honest calendar? What would an honest plan look like if you started now with hardware you could actually build and teams you could actually staff? Start with the conservative orbiter. Chemical propulsion plus smart assists. You pick a good Earth-Saturn window, you use interplanet flybys to lift your energy without oversized rockets, and you arrive with a capture you can execute. Cruise sits around 6 to 7 years. At Saturn, your insertion burn is on the order of 0.6 to 1 kilometer per second, squarely in Cassini territory. The win is payload, a mass-rich bus with real instruments, healthy power, a high-gain antenna sized for long range, and margin to survive dust, thermal swings, and radiation. The risk profile is known. The Tour can use Titan as a wrench to turn orbits for years, and the operations pacing is manageable. It's not flashy, it closes. Now the fast flyby with chemical plus Jupiter. You accept that you won't stop, you design for a burn-free pass, and you cash in time. With the right Jupiter phasing, you can hit Saturn in 3 to 4 years. The spacecraft carries a sharp pointing system, fast imagers, and a comms plan that can dump data over weeks after the encounter. You get high-resolution ring and moon imaging, magnetosphere sweeps, and atmospheric profiles, all at high relative speed. There's no capture fuel, no second chances. If you want that sprint, you tie your launch to Jupiter's position. You lock the geometry early, and you drill navigation discipline into the timeline. This is the option that delivers quick science and clean schedule, but it ends at outbound. Push into high C3 direct, still chemical. You buy departure energy with a heavy lift rocket and accept a thinner payload. No planetary assists, fewer mid-course events, a straighter path. An orbiter can come in around 5 years of cruise if you hold the line on mass, but the arrival burn grows, so the capture stage eats into instruments and margin. Navigation needs to be tight because you're running hotter at Saturn and your safe corridor narrows. This profile is attractive when you want to cut a year without scrapping an orbiter, but it lives on the mass cliff, 1 or 2 percentage points over target, and you start dropping capabilities you care about. Switch to an NTR-boosted orbiter. The game changes because every kilogram of hydrogen buys more velocity. With a nuclear thermal stage, credible designs put a Saturn orbiter in roughly 3 years, give or take the window. You can spend the efficiency on a hotter departure, or you can use it to show up cooler and ease the capture. Either way, the math relaxes compared to a chemical-only 5-year plan. You still face real gates, hydrogen boil-off over long coasts, reactor restart reliability, shielding, and ground test maturity, but none of those are fantasy problems. If you're aiming for crude pathfinders later, or you have time-critical robotic science, this is the near-term lever that pulls the calendar down without turning the spacecraft into a husk. Take the extreme, a solar Oberth flyby. You dive inward, fire near the sun for a massive speed kick, and aim straight for Saturn with no intention to stop. If your heat shield, guidance, and staging choreography are first class, you can reach Saturn in 2 to 3 years with a compact probe. Science is strong, rings, atmosphere, fields, because arrival speed is high but survivable for sensors, and you can pre-program a dense sequence. The logistics are brutal. You carry thermal systems that can survive close solar passes, you accept autonomy during calm blackouts, and you keep the spacecraft small so the shield isn't impossible. For orbiters, this remains a stretch. For flybys, it's a real high-risk way to cut the clock almost in half. How do these stack when a program manager asks for one timeline and one bill? Conservative orbiter, 6 to 7 years, high science return, proven playbook, stable risk. Fast flyby with Jupiter, 3 to 4 years, maximum calendar win, narrow window, single-shot science. High C3 direct orbiter, about 5 years, thinner payload, bigger SOI burn, requires a serious launcher and tight ops. NTR orbiter, near 3 years, better mass balance, engineering maturity required, but no new physics. Solar Oberth flyby, 2 to 3 years, small probe, extreme thermal and guidance demands, capture off the table. Each option moves the sliders, time, mass, risk, complexity, in different ways, and the wrong shortcut shows up at Saturn as an arrival your team cannot survive. There are hybrids worth calling out. A moderate C3 bump plus one interplanet assist can trim months without crushing payload. A small Oberth kick layered onto an NTR stage can bring a 3 and change plan into the high 2s for a lean orbiter, while keeping arrival manageable. A Titan aerocapture for cargo can pre-place propellant and supplies, letting the main orbiter arrive hotter yet still capture propulsively with lighter tanks. These mixes are where modern mission design often lands. Shave calendar a bit here, protect capture there, lean on Titan to clean up geometry once you're bound. Budget and ground truth finish the story. Faster timelines demand bigger rockets, thicker heat shields, or advanced stages. They also lock you into narrower launch dates. Conservative timelines open cheaper vehicles and wider windows. DSN time, tracking coverage, thermal test campaigns, and long lead components each push in different directions. The plan that wins is the one that closes across energy, mass, risk, and money, not just the one with the shortest number on a slide. So, with the scenarios on the table, what is the blunt bottom line you can trust? The range that summarizes flyby, orbiter, and bleeding-edge plays without hand-waving? And why do most smart designs settle into the same few-year bands no matter how you argue it? So, what's the number you can actually circle on a calendar? Here's the blunt answer. If you refuse to stop and you catch the right gravity assists, a Saturn flyby lands in about 3 to 4 years. We've already done that class of speed. Voyager 1 crossed Earth to Saturn in roughly 3.2 years, Voyager 2 in about 4.0. No capture, maximum data in a short window, then you're gone. That's already half the slow 6-year minimum energy idea people expect, and it proves that alignment plus borrowed momentum beats brute force. The cost is obvious. You don't live there, and you get the time you get during a single pass, which is why this option is for sprints, not long campaigns. If you want to stay, your clock changes. A practical orbiter with chemical propulsion and assists sits around 6 to 7 years of cruise. That's the Cassini lane, and it exists for a reason. You arrive with a manageable excess speed, you perform a serious insertion burn on the order of hundreds of meters per second, and you keep enough mass for real instruments, power, and shielding. You then spend weeks to months shaping the first orbits, scheduling ring plane crossings when debris risk is lower, and using Titan flybys to retarget. It is slower than the sprint, but it's how you get a decade of science instead of a day. Could you trim that? Yes, but every shortcut has a bill. Push a high C3 no-assist trajectory, and you can compress an orbiter toward roughly 5 years, but payload shrinks and the capture burn grows. Dive sunward for a solar Oberth kick, and a small flyby probe can plausibly hit Saturn in 2 to 3 years, but the heat shield, guidance at perihelion, and autonomy requirements go from hard to brutal, and capture is off the table. Switch to new propulsion and the trade shifts again. Nuclear thermal can double efficiency over chemical, turning a 6 to 7 year plan into something more like 2.5 to 4 for an orbiter, depending on window and staging. Nuclear electric, at around megawatt scale, can thrust continuously, beat Hohmann by years, and arrive cooler for capture, but it asks you to build a reliable space power plant with big radiators and long-life thrusters. These futures are aggressive. They move the schedule and they add engineering gates that you must clear before the numbers mean anything. Why does this shatter intuition? Because distance is only Act 1. You are not driving across a map, you are changing orbits in a gravity field. Energy sets how stretched your solar path is. Alignment decides whether you can borrow momentum from other planets. Arrival constraints determine whether your fast plan ends with a burn you can actually fly, a heat load you can actually survive, and an approach corridor that avoids ring dust at the worst moment. When those pieces line up, the calendar bends. When they don't, speed turns into risk, and risk turns into mission loss. So here is the headline you can use without hand-waving. How long would it really take? With today's tech and realistic budgets, about 3 to 4 years for a fast flyby and about 6 to 7 years for a workhorse orbiter. If you accept trimmed payloads, harsh environments, or advanced propulsion, you can push certain profiles down toward 2 to 3 years for mostly flybys, possibly for very lean orbiters with bold braking strategies. The number you pick is not just preference, it is a commitment to an energy, an assist plan, and an arrival you can survive. One more check before you lock anything in. The best-looking time on a slide can hide a capture burn that eats your margin, or a launch window that only opens once in years, or a ring season that makes your prime science impossible. The smart choice starts with the science you refuse to cut, folds in the energy you can actually buy, then honors the arrival you can actually fly. Do that and your really stops being a guess and becomes a schedule you can defend. So after all the knobs, assists, C3, Oberth dives, electric thrust, nuclear thermal, what does a clean example timeline look like start to finish, from launch week to Saturn Orbit Insertion to first prime science passes with the real buffers and margins left in, and where do most missions quietly lose months they never planned to lose? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.